second. Sorry, that was the presentation I gave here. Here, what I try to do is there are 4 P's one has to address. The challenges, if you look at a product development or technology development, it is a cycle. So one has to go through research stage, then technology stage, then training and absorption, and then to applications. So there are 4 P's. One is product, process, people, and production. Basically, I try to address what are these challenges when you look at taking a technology to industries. Maybe if yesterday I think Professor Ghosh clearly mentioned, the translation term is not so popular in engineering. It is more popular in the biomedical. But in engineering, usually we call it as basic research, applied research, pre-production parts, and then the regular production. Just for recalling, or maybe you can do at the end of the concept for the students. What is the definition? Like translational research is the same what Professor Ghosh mentioned yesterday. But the focus is translational research and applied research. If you look at the focus of translational research is to understand the mechanism of diseases and health related issues. That is what the biomedical, that is the research, that is well known. And then if you look at applied research is most of problem solving. So we CMTI primarily focused on this. Problem solving with finding immediate solutions to the industry or the stakeholders or the users. But there is a similarity between these two. That similarity is both translational and applied research aim to have practical solutions. So now there are also attempts, if you go through the literature, scan through the literature, there is also ways to measure this. So more popular now TRL levels. If you go to any funding agency, they will ask you what is your technology, what is its TRL level, and what you are wanted to target after the completion of the project. And also there are a lot of confusions. There are TRL, MRL, SRL, and IRL. So there are so many other confusions are created. In fact, our Government of India, through CAI, I am also part of that committee, they try to now redefine all these confusions, TRL, SRL, MRL, particularly keeping the funding patterns, because many funding agencies now, TRL become kind of major challenge, right? Maybe this table gives you little clarity on this TRL, MRL for science and engineering. So TRL 1, 2, 3, then to 6, it clearly says. And similarly, if you look at the software, we used to write alpha, beta, gamma, alpha version, beta version, gamma version. So now they are mapped to TRL levels. Then if you look at a medical research, they called, basically they called T1, T2, T3. Yes. The basic research, preclinical, then phase trials, phase 1, phase 2, phase 3 trials, right? But if you look at this one, this last slide I try to kind of combine a simple term like research phase is maybe up to TRL 3, and then translational development phase. Development means your research into a product or the technology which basically the investor is interested, and then the commercialization aspect. So once you are implemented, then you take the customer feedback, then basically your value, the product is value-added product for a specific application or specific domain that generates the revenue. So there are research, then translational or applied research, whatever you call, then the commercialization. So accordingly, correspondingly, you can map it. But otherwise, there is also ISO start has recognized this. In 2013, TRL has been mapped. So TRL 1 is basic principles observed in the laboratory. Then the technology concept formulated. Then experimental, the proof of concept, that they called it as a research phase. And then technology validated in the laboratory in the relevant environment, depending on at what conditions you are validating. That they call it as a development phase. Then the deployment phase. There are 3 phases. This is as per ISO 16220. It was published in 2013. So then if you look at product development or technology development cycle, actually there are three components. So you need to find the solution for a specific problem that usually starts with the board, drawing board or your simple AutoCAD sketches. So that is the design here, right? But finally the valuation happens over the material through a set of process technology, right? Say at the time of material, there may be, say for example, this is a rotary actuator which is used in HCA, right? So you are looking for a special material, and also with respect to the design, it has meant for specific purpose. So that means you are trying to address the challenges with respect to product design. And second is the product design is driven by these two parameters, that is the material and the process technology which you use, right? So you need, once you design, I will share this example, this product we have developed for LCA, right, gate rotary actuator. Just you mention this material, right? This material is not available in the country. We imported the material, and the guy who supplied the material is not ready to give a C certificate, there is a certification. The reason is he must have get it done through somebody, and or with certificate he cannot supply. There is always such, there are challenges. Now our certifying body, so we laboratory we proved. Now our certifying body, they are asking unless you certify that material certificate, so they cannot do it. So these are the typical challenges one has to address. Okay, one is component, design, all things happen, but major challenge is when you look at a translational research, you need to address those aspects. So still last 6 months we are trying to get the certified material. Now certified material is not available. So similarly, process, if you look at, just listed related to additive manufacturing, there are additive manufacturing itself has its own challenges, right? So product, I will give you, I think there is a separate slide is there, but this is the point we are going to address in the translation research. Before that, when the design stage, so prototyping is the kind of, you can't avoid. Okay, that prototype may be a CAD model, or you do some motion simulation in some of the software, right? So depending on what we are focusing, and prototypes are also classified like physical versus analytical, then focus versus comprehensive. The moment come to this, right, here you need to have a physical prototype, that too many times it is a pre-production part of same material produced through same manufacturing process. That means by the time you come to this stage, you are already committing. So typical, the graph, if you remember in product development textbook, 80-20. The progress, physical progress is 20, but you are committing on 80% of the cost. So that those things you have to address. So to some extent, to large extent, now this problem has been minimized because of this technology like digital twin technology. If you look at smart manufacturing industry 4 guys, now they are talking about digital twin. So this is the digital twin developed at CMTI, just I'm showing picture. This is for the stages, drives which are required in CNC machine. So those things facilitate, which reduce this, but still on the translation stage, there are a lot of challenges with respect to the product and as well as the process. So then what challenges we address, I just listed, is that a lot of text is there. So if you look at a product, you have to look at whether it is innovative and how it is different from your competitor. Not necessarily that your product is completely new product. So, but yesterday, if your Professor Mark was giving that gamma and lambda, these are all compared to the competitor products, right? So that you need to address in the lab level itself when you are working on the lab. So we need to look at those aspects, how innovative it is, if it is not innovative, or if it is differentiated. Then the market adoption. So market adoption is, say for example, the product which is meant for, if you look at industry 4, the meaning of industry 4 for ABB, the meaning of industry 4 for MSME somewhere is doing a job shop is entirely different. So right, you need to develop the product. Maybe your product is best product in the laboratory, but it may not be a best product on the shop floor, right? And then if you look at a process, then efficiency and optimization, then innovations in operations. The idea is, particularly nowadays after COVID, the cost of ownership of the product becomes the driver for innovation. So no luxury is applicable. Now everybody is looking at frugal engineering. If you go to Germany, I think there are 5 universities that have a department called frugal engineering department, right? So cost of ownership, if you look at, so naturally you need to be innovate in the process, because processing, that is where the raw material is getting transformed to a product. The value addition process happens, and the money investment happens at that stage. Then the people skill development, and then the cultural transformation, those aspects. The production, if you look at the capital, the scalability and capacity building, and the last one is sustainability and the responsibility. Who does what? So that is all, including the supply chain. So these challenges we need to address. In order to do this, I just you can remember this. I call it as a DISC approach. The product, process, people, production. So at the product stage, we are basically converting data into a design. So to convert data to design, there are several approaches, several tools. That means one has to look into the customization, mass customization or localization, new or novelty, then the frugal design aspects, then cost of ownership, and then when and why, because these all components are meant to meet some specific requirements. Then if you look at a process, then innovation to inclusion, you need to bring all the stakeholders in this manufacturing value chain, the value addition process. So you need to include them. And then if you come to the people, of course, it's a cooperate and collaborate, because cooperate and collaborate is important. The reason is, nowadays, no manufacturing houses, people doesn't believe that everything you manufacture in under one roof. It is always distributed manufacturing, and then you need to take care of, at least you should be ready to cooperate and also to collaborate. So right, so I think that is where you need to teach not only the technology but also to how to work, how to collaborate with the people. Then the scalability and sustainability, this is where the capital investment is there. So one has to look at the capital goods like machines, automations, then how do you harvest the technology or the knowledge which is generated at a different houses or the different R&D or academic institute. So at the end of the day, you need to enhance the productivity and you be sustainable, right? So that is what this is completely my slide. I thought copied. There's a lot of exercise. This is what my learning after moving to CMTI. So one, you need to consider like all these 4 that are called a DISC approach if you want to take the technology from the laboratory to the users. But the opportunity for us, for engineers, only these 5 F's. So in engineering will never be 1 + 1 will never be a 2. It's always either 2 + or 2 -. So one has to understand why it is 2 + or 2 -, and then what we can do as to move as close as 2. So that tools are there, only these tools. So F's, 5 F's, that is for where we deal with the geometry, motion, interfaces and all. Then functions, of course, it is every development, every activity we do has some meaning, some purpose. And then of course a lot of science behind it, so flow of mass, momentum, energy. And then the physics, here just to remember I made F, physics, it need not be physics, chemistry, biology, the science behind that. So then the fabrication. So sir, I don't know I'm correct or not, all together is called engineering science. This is what my understanding was. If somebody can address all these aspects by using scientific principles, so then there is no jugaad. Jugaad doesn't work. Jugaad meets the requirement, but it will not ensure you the sustainability and the repetitions. So if you just look at what, say for example, with respect to process, what changes happened in the process? So in the manufacturing, if you look at, apart from product design, so mostly the innovations happens with respect to manufacturing process, manufacturing of equipment, and manufacturing of systems and factories. This I borrowed from Professor Kapoor's slide. We developed when the Indo-US Fabrics program. right? So these three change developments happened, but now the new addition is these all happened, all are in an isolated way. So now people are looking at current manufacturing, the focus current or future manufacturing, they call it connected manufacturing, right? So by definition, if you Google connected manufacturing, this is a Google statement, right? A business strategy that uses cloud computing to harness operational business data in order to help manufacturers to improve their process. So this is what the connected manufacturing. Connected manufacturing means now the entire value chain, no activity happens in isolation. Yeah. So now, so we country, when we are looking at Atmanirbhar, right? So now, if you look at, we are at least fortunate. So we came out of this. Now, nothing made for India, right? So Make in India is just a process we started. Made in India, of course, if we technology developed in the country, so that brings the pride. But if you really look at Atmanirbhar, then we need to have the technology originated in India. Yeah, it was there. So best is it was not affordable to us. So naturally there were the components manufactured, meeting specific customer, that is Indian customer. So this is what now I think we are really, if you look at as a country, the technology originated in India is very low, and owning IP creation is still not the priority for us. So we need, if we really look at that IP creation, so naturally we need to work together. So this is for the material science people. I'm sorry this picture is, the thing is visible, but you read this reference. Production Technology Reader, the source is World Economic Forum. So this is one picture that clearly represents what all aspects has to be considered just for new material development. Right? So I just, some of the points I just taken out, I just explained here. Say for example, if you look at the new material development, so one has to look at how they are being processed, production process. Because you have developed a beautiful material, but we don't know the process technology. So how to add the value to that material. Second is human-machine interface, that is with respect to machine material safety. Then connectivity and computing, analytics, intelligence, digital physical transformation, production philosophy, and advanced material. So these are all there at the outer border. Then, okay, there are several materials, I'm sure you know better than me, several material happen. But one thing is common, this. Whatever the material you have developed here, so this has to meet functional requirement with the expected performance level. Then the design possibilities, because you are also designing a material to meet various requirements within the specific domain. So this is more of basic research, but when you do the translational research, I think we need to focus on this. Translational research on the material development. So one has to look at scalability and sustainability. Say for example, nanomaterial synthesis. I think if you go to any research lab, at least 2-3 research team focused on nanomaterials, but they can synthesize only 100 grams, 150 grams, 200 grams. So now how to do in the batches, at least in the batches of few kgs per shift. So right, so that kind of scalability you have to look at when you are engineering the material. Then cost optimization, of course I already mentioned safety and the compliances of specific standards, then the technological advancement. But this is just for one aspect, that is the new material development. This is applicable to all the manufacturing process. So let us look at the manufacturing process. If you look at the manufacturing process, you name any manufacturing process, so still all the manufacturing falls under these 4 categories. So we create some desired shape by removing a material, or we are shaping a material like with phase change, without phase change, you are casting, forming, all those processes. Then the additive manufacturing, deposition, coating, all those. So that means we are adding a material either over the substrate, or you are in case of additive manufacturing, you are adding a material to build a functional or ready to use component. Or the self-assembly, which yesterday again was mentioned in the presentation, right? So you are dealing at the atomic level. So you self-assembly, de-wetting, or there are different mechanisms to create the microstructures on nanostructure structure, even not on the metallurgical aspect, it is on the geometry wise. So these are few examples, just you can say. I think I have not found any manufacturing process which does it. Maybe Professor Mark may say where the biomanufacturing falls. I think biomanufacturing, I presume it still falls under this. Maybe the principle is different. Then let us look at the food, right? You can easily, I prepared this slide. The reason is food is easily, people can easily correlate, right? Normally, any food research innovations happens. This is the driving force. It should be healthy and nutrient products. You may ask why I get into food, because we are building additive manufacturing for food products. So now we got the project, we are building 3 machines for 3D printing of food products and medical nutrition. We are building machine, but the CMTI helps us to formulate the this one, chemistry behind these food products. Health and nutrition products, then better efficiency in food production, environmental and political impacts, and the reality and perception gaps, so mass customization and all. There are multiple, the idea is, so there are driving forces, there are multiple viewpoints. The multiple viewpoints are this. One is reducing waste, better control of equipment, enhancing customer experiences, then improving flexibility and accurate food safety. So whatever I marked black, there are solutions are already existing. So what is there in the red, still solutions are not there. Customer has not accepted some solutions. If you look at IoT and all is there, but still is not very well accepted before that. This is applicable to any domain. If you wanted to do research, so you can figure out what is the kind of viewpoints and the driving forces. Then try to identify the gap. So as a part of your research, you are only doing some percentage of the existing gaps. If you look at that, at least my learning from last 5 years is, so R&D is now changed instead of research and development, it's more of now relevance and delivery. So people, say for example, at least institute like us, there is no opportunity because everybody expects that the product you are or the machine you build, that should be delivered in the first time. And customers comes to CMTI, they will say, imported machine cost this much rupees. Can you supply it or can you develop at the cost of 1/3? And that product we never developed. So that is the kind of challenges we face. If you look at additive manufacturing, so why I said that there is no shortcut, it is always technology development happens S-curve. So it is invariably you have to follow S-curve. Okay, depending on the expertise, resource, and the team, that maybe angle may be altered, but it is invariably the S-curve. So additive manufacturing, I just look at, see, it is only Indian. If you look at additive manufacturing as a alternative or effective manufacturing process to use in industry, so still there are a lot of challenges. I think Professor Manna's last slide was that, right? If you look at in Indian status, so 1995 we already had a rapid prototyping machine in IIT Kanpur, Professor Dante introduced. 97 CMTI has a 3 RP machines, rapid prototyping machine, CMTI has a Kanpur, right? 95 to 2000, there were a lot of conferences and all happened. How to use this process technology. That time, additive manufacturing was not the term. Rapid prototyping or layered manufacturing, those are the terms people used to use. For initial few batches of productions, but this was not great success in India. The reason is, as I mentioned, we are still not very good in terms of the design, original design of a product. So then there are a lot of efforts globally, including in India, it happened. Can we use this, if not for prototyping, at least for a pre-production process, So that is what they called rapid tooling. That means making molds, dies, using this layered manufacturing, and few batches of the components could be produced in a very shorter time. That was like 2000, 2012. Next 10 years was primarily in India. We focused on that. So thereafter, I think it was gone down. The only different reason was the material. We didn't have a material. There were a lot of restrictions. Machines, for example, EOS Germany DMLS process, they had only two machines. That is a direct metal, one direct metal two, that is copper bronze kind of combination. And they were not, since this technology developed elsewhere, they are never allowed researchers to use the different material. That was in my own experience because I did PhD in this area. So I wanted to use a different material, that too, because I want to make an injection mold, molds out of this. Injection mold means at least P18, P620. Otherwise H1, H2, sorry, H11 or H13. So none of, only one facility that time it was in CMTI. They never allowed because the warranty is allowed only if we use the material of described by EOS German. So that kind of restrictions were there. Making a mold dies on same material and all was a challenge. Now, so 2012 to the future is, can we use this now? Again, last 5-6 years, you look at almost every day there is some, in city like Bangaluru, there are 3-4 conferences on additive manufacturing. Every day you can look at, right? So the focus is technology. If you look at the technology development, fundamentally technology is not much developed, rather it is fine-tuned. So when this was there, there were 10 rapid prototyping processes. Now only 3-4 technology people are reached to that level, that technology is a readiness level 7 to 8, where the manufacturing could be used as a manufacturing process. But a lot of things happened with respect to process, with respect to lasers, and with respect to the understanding. So now people are looking at, can we use this AM for a regular production, if not as an alternative manufacturing process. So, but still there is a challenge, as sir you rightly said, that red line. So red line is still a relative. The reason, particularly for the Indians, this is an expensive because machines built elsewhere are expensive. Material sourced from elsewhere is again not cost competitive when you look at, unless. So
one thing is generally not considered.
Yeah.
In production process, we always concentrate on the shape generation of the part. But the nastiest part is the assembly.
Yeah.
So the real benefit which can come through this generative process is that you can make multi-component part in the same process. So assembly part is gone. How that is taken care of in the cost analysis, that I have not seen.
Yeah. So there are two aspects into that. One is that there are two challenges. One is all the components which are designed now, they're all designed for either rolled, cast or forged component. Now, the clear understanding, I don't know, maybe Professor Manna has a different perspective, but my perspective is still design engineers doesn't have a sufficient data. The components which were otherwise designed for rolling or forged, can I replace with 3M made components? Even if you scan the literature, there is a different story, and some literature says DED, at least I'm knowing DED, our people are working. So DED made components are better than the forged component.
The characteristics.
Still it is not there. And even the ISO standard, now ISO has adopted 7 standards with respect to AAM. Out of 7, 2 BIS is also adopted. But still the question is, though I am not material testing expert, whether the tensile test experiments which we conducted, so the one basic understanding was that microstructures that should be homogeneous. So now if the same test is applied for additive manufacturing components, whether it can be validated or not. In fact, this question was asked by Semilac Kai.
Another thing, could you kindly explain, because you are in these committees, what exactly meant by Make in India? Because the industry, as you very correctly said, now it is not under one roof.
Yeah.
Actually, now it is not in one country.
Yes, true.
A large number of machines or systems or devices you will find different components are made in different
parts.
But which is then the country will make in India? What does it mean?
So I don't know whether it is public domain I can speak, but the idea is that the original concept Make in India was invitation extended to so invitation extended for the global leaders to establish the factory and make the components within the country. They can generate the employment, and at the same time technology can be disseminated. But later on now that little deformed, kind of people have realized, so can we develop the technology within the country while working with the global leaders?
No, but maybe you can suggest that we should consider that part, that step, where the value addition is maximum.
Yeah, that's true.
That should be in India.
I think that is what the focus is now changing. In fact, Atmanirbhar is primarily derivative of this Make in India, I think. So in between we just Made in India, but yes, there is basically the focus is, the overall focus is if you really wanted to become a leader, ultimately I have to create an IP. So that is what IP creation is now, at least people are talking. There are same things, for example, if you look at additive manufacturing, so with respect to product, there are still restrictions with respect to geometry, tolerances, minimum feature, what we can able to build. And more than that, we need to develop a strategy for designing an AM. So designing an AM needs lot of data with respect to material and then the testing and then the qualification processes. Because whether the same thing is applicable, that we need to debate. The process, there are majority of the process, but every process has advantage and a disadvantage. So because they are all developed parallelly, there is still low maturity level. So okay, there are process, X material could be made which is ready to use, but that may not, the same process may not be used for the Y material. I think there are low maturity level, then still this process is a slow process. Additive manufacturing still is not a rapid manufacturing. If you look at it as an industry production process, so naturally you need to use this process selectively, value-added component. That is why there are a lot of emphasis going on aerospace and space. Requirement is one-off, and their rupee is not the matter. But if you look at general engineering, component manufacturing suppliers, they are operating with 10 paisa. Margin is they are operating with 10 paisa. So that is how naturally the additive manufacturing is long way to go reach to general engineering manufacturing, component manufacturing. Then the training still, except a few IITs, National Institute, additive manufacturing is still not a course. It is just remain as an elective course. Then production is, this is I think where we need to focus. If really additive manufacturing has to be looked at as an alternative manufacturing, so naturally we need to build machines, we need to develop materials, and then we need to work on the design for AM so that there is a new design meant for additive manufacturing process. I think these are all the challenges with respect to additive manufacturing. I think there is the same. So looks at product design, redesign. Then may not that any design you make, AM can able to make it now. Then there are a lot of restrictions with respect to materials. Then reusability. So there are, when you are looking at because biomedical is another area where AM has a good potential, but there is no knowledge is there whether reusability of AM made components. So say for example 15 minutes auto cycle, autoclave, we do the surgical tools, whether that is good enough, those kind of challenges, because there is no data on this. Then quality of the parts produced by AM, as I said, okay, surface finish is one, people are working on finishing of surface AM components, but still making a sharp components, sharp geometry like 90-degree kind of things is still challenge in the AM because there are restrictions. Then of course all the AM machines right now size limit, though there are robotic arm based processes are there, but typically AM machines are 300 by 300. But when I look at a large component, say for example now we are building a DED machine of 2000 millimeters, that is 2 meter by 1.2 meter. So now challenge is that a lot of metallurgy challenges. So because I have to scan it, there are different scanning strategies there, but the heat when I start the process for one, starting from 0 to 2000 millimeter, whether that is same process condition will not be there. So now how it metallurgically affects, so we don't know. I think that is what the challenge we are facing now. We are working on PKM based machine. So like that there are several challenges, but otherwise yes, that is how once we know the problem, then we can able to define, find a solutions. That is what basically I wanted to say. There's a rest all I will show what CMTI does in line to my discussion. The idea is when you are looking for a product development or that to translational research, so you need to address this 4P related challenges, and these 4P related challenges has to be addressed not at the IRTRL. It is better if you can able to bring into the laboratory. I think that is what the change is required. Otherwise, what will happen is our majority of the research ends with the publications. We CMTI, we basically try to fill that gap. We primarily work on applied research, particularly if you look at a TRL term, 3 and above. These are our domains, different domains. We build machines, ultra precision machine tools which are capable of creating micro nanoscale features. And then we build a special purpose machine. Special purpose machines means for any applications, we build a textile machine, and we also build a machine like this to mix the solid propellant which used in our space aircraft. If you look at all these things, CMTI is one, that is where basically we are different. We build a machine which are ready to use, that the first time, and we have not built any machines which are new to world. But whatever the machine we build in the country, they are first time in the country. So still none of these machines were built by anybody else. Last 60 years we built such around 500 such machines. Usually we built around 10 machines. At least since I took over, we built 30 machines. All these 30 machines are new machines, and all these 30 machines are supplied to our customers. So that is how we work. Apart from that, yes, we do some services, testing services, then design consultancy and all. And we also conduct some of the practice-based training, which is all short-term training, like we call it as skilling and reskilling. And then right now, after I moved, because earlier CMTI used to work like a service provider. Now we have created a technology marketing group. So we try to protect the technology, then transfer. I think we transferred recently the 2 technologies. These are the few machines, like about 30 major machines we developed last 5 years. And we also transfer this technology. If you look at, okay, these are the one we feel proud. The reason is we supply 24 such mixing machines. These are required to mix the solid propellant. Of up to 4.5 ton, we already supplied 24 machines to various strategic sectors, DRDO labs and ISRO. And now our 25th machine is the 10-ton capacity machine. This is the highest capacity in terms of volume of mixer ever built globally. And this machine just last month, August 17th, we hand over. Chandrayana, say for example, Chandrayana, if you look at, we supplied 4.5 machines, several machines. You may be knowing rocket motors has 3 fuels. One is solid propellant, liquid propellant and cryogenic. Chandrayana 3 carried 400 ton solid propellant. And thus the 400 ton solid propellant was prepared by mixer machine which we supplied, using our mixer machine. Last 12 years now, no import has happened, and we kind of a monopoly in this. This is also 10 ton which we hand over to ISRO. This is one technology we feel proud because it happened recently. So we transferred this technology to now ACE Designer. It's a diamond turning machine, which we installed 2 machines in the park. Then our industry ACE Designer who came forward and we transferred the technology. This is another rapier loom, high-speed rapier loom for weaving a machine. That's what I'm saying. We build a textile machine. Also, we build this machine. These all comes under special category. This rapier loom, you may be knowing that still the India uses looms, power looms primarily, hand looms and power looms. Even in mechanized high-speed rapier looms, which they use, is only 200 to 250. If you go to Surat, whatever they are there, they're all retrofitted looms. coming from China. Now we supplied, we designed 450 speed. That means is rapier, is 450 times it picks, rapier moves in a minute, that speed. And we transferred this technology to 5 companies. And one of the company, Surat-based company, they commercialized this, they launched as their product. With this, the kind of advantage impact is, though we supplied a machine with just one sub-development of 10 ton, ISRO saved 140 crore. Because in 2019, when the project started, ISRO got a budgetary offer from US. Because globally only 2 companies makes such kind of high capacity mixers. 120 crore for one machine. And we designed, developed, supplied 2 machines in 100 crore, not even 100 crore because of the central limit, 99 point something. So that means 140 crore is the net saving to ISRO. So similarly, if you look at this machine, diamond turning machine, our immediate competitor is Precision. Precision, even when I was in CMTI, I wanted to buy this machine. That time it was 6.5 crore was the quote. Once we started developing and CMTI already installed this machine, 2 machines in bar. Now this company is transferred. I'm 100% sure we supplied 3.3 crore to ISRO, sorry, to bar. They will, I'm sure they will commercialize less than 3 crore, right? So net saving is 1.5 crore per machine. So because now Precision offering 4.5, 4.8. Earlier they used to offer 6.5 because now since it is technology is available in the country. I think that is why the machines developed. This rapier loom is also saved. So our rapier loom, this rapier loom is just 60 lakhs rupees. Our developmental cost, I'm sure he will supply, is almost starting already 40 crores or 40 lakhs. So while doing machine development, what we took, as I said, we have never built any machine which is new to the world, but we built, whatever the machine we built, that was first time in India. But while doing this, our focus is we try to indigenize the subsystems. Because these are all AI technology, there are a lot of challenges, subsystems which are many times the global leader block that. They will not supply the subsystems. So for that purpose, what we are trying to do is all these subsystems which are very critical. So we will develop total package. Now we given 5 technology package to S Designer. So S Designer can commercialize this machine and no need to depend on any imports. All the major subsystems are there. Even assembly test protocol, we CMTI only takes care till now. So like that, basically the strategy so that we can, our licensing basically, you don't need to depend on the subsystems. Particularly the IA technology, this is the challenge. And this is additive manufacturing, that stereolithography, SLA. This is a machine, so you know SLA, microstereolithography would cost you about 1.2 crore. Academic price itself is about 1 crore. We are now selling this machine 37 lakhs. Yes. So that is a kind of advantage with the machines designed, developed by within the country. Another like Industry 4, so we are basically, you may be knowing MHA, there was a scheme, Summer Center. We are one of the center. There is a smart factory we created, and we have developed about 11 solutions, and we implemented small scale company as well as the bigger company like Toyota Engine Division. This is one example. I think this is just to show that this is going to come. We already supplied. We are just waiting for the installation. That is a smart foundry. This was a DST project we developed. This is a smart foundry, means it is basically is IIoT enabled system, miniaturized foundry with a footprint of 16 feet by 8 feet. It allows you to cast 1 kg aluminum casting, and the machine is designed, developed by our own team, and then it is integrated with the sensor to address the challenges of this typical sat casting environment. Okay, this is our team, so multi-institutional team, and then this is the system we have supplied already. So we are waiting for the installation at MIT. So thanks to your director. Yes, because this is, I know it is a research developed product. So naturally he has accepted. We will install. So that becomes kind of baby test bed for you people. So I think I will stop it here. There are several other technology we developed with respect to aerospace. This is, as I said, gain rotary actuator, if you look at some internal views. And we also developed a pump, axial piston pump. Though we started as a learning exercise, that time CFD analysis was getting done through Jadavpur Institute. But now that becomes the technological requirement because of Ukraine, because this pump used to come from Ukraine. Because of the war, now it's stopped. So India need 150 such pumps. So already manufacturing rights are assigned to HAL. And this is the new journey. We have created a facility. So now this can process 6-inch wafer. We can build up to 600 micron feature. That is the resolution what we are talking. If any such requirements are there, so still this facility is not fully utilized. We can able to supply services starting from design to packaging. So in one roof we can start with the design, then we get a sensor out of that. So the complete system, we have all the tools, but all the tools are independent tools because idea was to supporting the R&D team. It is not a production factory, but few hundreds we can easily do. And this is of course reverse engineering, scanners and all. This is just yeah. Next coming maybe like another. We are there is an industry accelerator. So we closely work with 13 industries. We are developing 16 products. These are the current projects. These all 16 machines what we identified, machines are delegated. Again, they are not available in the country yet, not developed. So just close. Thank you. Thank you.
Take one question. If it is. Okay.
Sir.
This is very impressive. I was wondering how, when you place these complicated systems, the buyer often will choose the equipment based on the servers they get. The machine breaks down, and a team very quickly comes to fix it. In the way you're working, can you provide that?
Yeah, it was, as I said, basically we are initially working as a service center. Service means you come with a problem and we make a machine and give it to you. Then now what we have done is, there are two models we work. One model is, okay, you have a problem, you define, you are looking for a solution with respect to machine process. We design, develop and install at your place and we will maintain, lifetime. We will maintain. If you buy our technology, so by means some other industry, usually we will assign the rights to them and they will supply and maintain.
This becomes very expensive and then also for you,
Yeah.
Because you need to send your engineers to these places, stay there for a couple of days, sometimes a week.
Yeah. That if you look at ROI or revenue generation, yes, this is a challenge. But what we are trying is, being a public funded institute, there are two aspects we are looking. We are interested in AMC because we have to self-sustain. So that brings some continuous revenue generation. And at the same time, we feel that it is our duty to support industry. Being a public funded institute, I cannot say no to industry if really industry wants it. So we are offering. In fact, the machines which we design, develop, normally we get a standard warranty. If you want to buy a machine, I will maintain 5 years. That is even in selling order itself we will commit. Usually imported machines, if you look at standard warranty is 12 years from date of installment, 12 months from date of installment, otherwise 15 months from date of supply. But we give 5 years warranty.
Still you are not making which are electronically intensive
Yes, sir. So if you look at our diamond turning machine, it is in all senses a smart machine.
So where are we getting the chips?
Chips and all we buy right now. So primarily we outsource. Sometimes we design our own, right now because of the sensor. It is only 3 years.
No, because in India now there are quite a few institutions they are designing VLSI chips. So these are not extremely complicated,
Yes.
but they can go to sub-micron level.
Yeah.
So are you also?
Yeah, now I think earlier we didn't have a kind of facility, fabrication facility. So normally we captured of some
Like I saw recently, I was mentioning Parag, IIT Mandi has a facility to go to deep sub-micron level in making VLSI.
Yeah, right now that's what I said. We have our facility also allows up to 600 micron, 600 nanometer, 0.6 micron. So we have.
Yeah, just to continue the question with the Mahmoud, how you are taking the making the policy for selling your system to government organization? Do you need to go for again tendering process and all these complications, or do you have any kind of?
See, that is you have to decide whether you go for tendering or not. But as a seller, I am participating through bidding.
Oh, you are participating.
Bidding. I am a registered seller of GEM portal. But at the same time, if you look at high-end technology, whatever we develop, the strategic sector and all, we are all certified supplier. So they directly come to us. We involved in the design stage itself, because many times they are not able to define the product specifications. We involved from that stage, and then we do. Because they certified CMTI as a registered supplier. Yes, that is also. But otherwise, if there is an issue, we participate in one in GEM. Yes. In this case also we are trying to resolve without.
Thank you, sir. We were aware of material science tetrahedron, then he taught us 4P. We learned 5S in industry, and now he taught us 5Fs. And so the PPT provided actually a roadmap to connect academia to the manufacturing setup. Yes, sir, please.
Thank you, Dr.N.Hanumaiah, for this elegant lecture. So I want to add one thing here. Actually, we have created a roadmap for our institute. Professor Amitabh Ghosh was there in the committee, Dr. Manav was there. And our primary objective was to translate digital advancement into manufacturing, and in other way around, manufacturing into digital advancements. Basically, when you translate, it is between two languages, and you need to know both the language. So we wanted to approach in that direction, and in that direction, now we have an MOU with CMTI, where we are creating a digital manufacturing facility within a budget of about 6 crore. And it is, to answer your question, actually when you buy from some government organization under ministry, you need not to go through, tender. But you have to agree with the advance payment terms. Because the limitation with CMTI is that, for a big budget, they don't have the fund to create the whole system for you and to get the money. So there we need to fix some agreement on advance payment. But we are doing that, we are already in progress, we are going to place the order, and our infrastructure is also ready. So it is kind of a digital manufacturing. Not really, sir.
It has to be open.
Yeah.
Usually.
So there is effectively
It is clearly defined in government finance rule, which is Bible for us. So we are doing according to that, but yes, we have advanced considerably. Thank you.
Thank you. I request Mark Madhav sir to felicitate Naga sir on behalf of TRM in 2023. Thank you. Thank you, sir. now we are going to start with the next session. Maybe few minutes, please. So let me introduce to the next keynote speaker, Dr. Mamila Ravi Shankar. He is currently an associate professor in the Department of Mechanical Engineering at IIT Jubilee. He has published over 60 internationally reputed papers and 100 international conference papers. He has 7 patents to his name, 2 edited books and 13 book chapters. He is recipient of prestigious awards such as Institution of Engineers India Young Engineer Award 2015 in Production Engineering, Indian Society for Advancements in Materials and Process Engineering. There are many accolades to his name, but he is insisting on cut short introduction. Yeah, and he is a weightlifting champion as well. So that adds to his profile. So thank you, sir, for joining us. Thank you, Manna, sir, for joining us. It was nice. Thank you, sir. So we'll continue with the lecture from Ravi Shankar, sir. Thank you.
कभी कुछ